Have you ever looked across a freshly poured, perfectly smooth concrete slab and felt that quiet sense of satisfaction? I know I have. There's something deeply grounding about combining earth, water, and stone, then watching that mixture transform into a rock-solid foundation that feels as if it could outlast us. In a world that constantly changes, we build because we want something permanent. Then, just a few days later, you step outside with your morning coffee and suddenly notice it. A thin, jagged line stretching across that beautiful new patio. A crack, and it hits you right in the gut. Did you mix the concrete incorrectly? Did you start troweling too soon? Here's the hard truth. The fate of that crack was often determined within the first few hours after the concrete was poured, while the surface still looked wet, smooth, and flawless. By the time the crack finally became visible, the damage had already been developing for days. To understand why, we need to look at what extreme summer heat was doing to your slab while you were standing there admiring it. Think about the last time you had a serious sunburn. You were outside, the sunshine felt good, nothing hurt, and you had no reason to believe anything was wrong. Only hours later did the redness and pain finally appear on your skin. Fresh concrete experiences something remarkably similar. The same conditions that burn your skin, intense heat, direct sunlight, low humidity, and wind, can devastate a newly poured slab. So how do professionals working in desert climates like Arizona, Texas, or India pour concrete in 100-degree weather and still produce smooth, strong, rock-solid results? Today, we're going deep into the chemistry of cement, the physics of water, and the time-tested craft of building things that remain intact. Whether you're pouring a walkway, a cabin foundation, or a driveway, this is what you need to understand if you want to keep summer heat from destroying your work. Let's dive in. Part 1. The exothermic beast within. If you want to understand concrete, the first thing you need to do is stop thinking of it as simply drying. Concrete hardens through an irreversible chemical reaction called hydration. The instant water comes into contact with cement, a chemical marriage begins, and that reaction generates heat from inside the concrete itself. Deep within the mixture, calcium compounds in the cement react with water and begin forming calcium silicate hydrate, better known as CSH gel. This CSH develops into millions of microscopic, needle-like crystals that grow outward from individual cement grains and lock themselves around the sand and gravel. That interlocking network is what transforms a muddy, workable mixture into solid stone. But during the summer, this chemical marriage can become chaotic. Heat acts like an aggressive catalyst. As temperatures rise, cement compounds, especially tricalcium silicate or C3S, begin reacting much faster. At around 70 degrees Fahrenheit, concrete may give you a comfortable 4-hour window for placing and finishing. At 90 degrees Fahrenheit, that working window can collapse to roughly 2.5 hours. For every 10 degrees Fahrenheit rise in temperature, setting time can decrease by approximately 30%. And that rushed reaction creates a serious weakness. Instead of forming an orderly, durable internal structure, the CSH develops rapidly into a more disorganized and porous structure. This creates what is known as the crossover effect. Extreme heat accelerates early strength, so after only 1 or 2 days, the slab may look fantastic and feel incredibly solid. But don't let that early strength fool you. Because of that porous microstructure, the concrete's ultimate 28-day compressive strength can fall by 10% to 25%. The foundation appears to gain strength quickly, but it pays for that speed, with reduced long-term durability. So the real question becomes, how do we slow down this exothermic beast when the summer sun is doing everything it can to accelerate it? Part 2. The silent thief, plastic shrinkage. While chemical reactions are racing inside the slab, another battle is happening right at the surface. This is where plastic shrinkage cracking begins. When fresh concrete is placed, it naturally goes through a process known as bleeding. The heavier components settle downward, forcing excess water upward until a thin, wet sheen appears across the surface. That bleed water is extremely important because it keeps the surface humidity near 100%, protecting the fresh cement paste underneath from drying too quickly. But summer conditions can completely disrupt that protection. If water begins evaporating from the surface faster than bleed water can rise from below, that protective sheen disappears. Now the surface begins drying while the concrete beneath it is still soft and plastic. As water evaporates, negative capillary pressure develops within the surface paste. That pressure pulls particles together with tremendous force. The problem is that fresh, green concrete has almost no tensile strength. So when those shrinking forces become strong enough, the surface simply tears apart, producing long parallel cracks or irregular map-like patterns. The ACI 305R guide considers 4 major factors when estimating this evaporation rate: air temperature, relative humidity, wind speed, and the temperature of the concrete itself. The critical evaporation threshold is about 0.2 pounds per square foot per hour. Once evaporation rises above that level, plastic shrinkage cracking becomes extremely difficult to avoid. And on a hot, dry, windy summer day, evaporation can easily climb to 0.5 pounds per square foot per hour or more. At that point, without immediate action, you are fighting a battle that becomes almost impossible to win. Modern blended cements create another challenge. With materials such as Type 1L cement, the fine limestone content can reduce bleeding. That means the safety threshold may fall to only 0.1 pounds per square foot per hour. Using modern materials while relying on old assumptions is a recipe for failure. Part 3. The early strength trap. The early strength trap, better known as the crossover effect, has fooled countless builders. At around 100 degrees Fahrenheit, or 38 degrees Celsius, hydration accelerates dramatically. Concrete sets quickly, and may already feel extremely solid within 24 hours. After 3 or 7 days, concrete cured in hot conditions can actually show higher compressive strength than concrete cured at around 73 degrees Fahrenheit. And that is exactly what makes this trap so dangerous. That impressive early strength is an illusion. When hydration happens too rapidly, reaction products are deposited chaotically around each cement grain. Instead of developing evenly, they form a dense, localized shell around the grain's core. Eventually, that shell becomes a barrier. Water has difficulty reaching the unhydrated cement trapped inside. At the same time, rapid evaporation removes even more moisture from the slab. Slower reacting minerals, such as dicalcium silicate or C2S, which play an important role in long-term strength, can stop hydrating because they are starved of the water they need. Then, around 28 days, the crossover becomes obvious. The concrete that looked stronger during its first few days can fail to achieve its intended design strength, losing roughly 10 to 25% of its ultimate capacity. What remains is a more porous internal structure, filled with capillary voids. That porous matrix can turn your slab into something much closer to a sponge. Water penetrates more easily, then freezes, expands, and gradually damages the surface over time. A fast beginning can lead to a weak finish. Real strength needs time to develop. Part 4. The subgrade trap. The enemy from below. Some of the worst concrete failures don't begin on the surface at all. They begin directly beneath your feet. This is the subgrade trap. Before pouring concrete, you prepare the base underneath it. But during the summer, that gravel or soil can become extremely hot, dry, and thirsty. Pour fresh concrete directly onto that dry subgrade, and you create a battle on 2 fronts. The sun begins pulling moisture from the top of the slab, while the thirsty ground underneath begins sucking moisture from the bottom. Your fresh concrete is losing essential water from both directions at the same time. That uneven moisture loss creates shrinkage differences and curling stresses. If the bottom of the concrete loses water too quickly, the cement paste cannot hydrate correctly or develop a strong bond around the aggregates. The result can be a weak, dusty, poorly hydrated layer along the bottom of the slab. exactly where you do not want weakness when traffic and loads begin pressing down from above. So what's the solution? You need to soak the subgrade, but you need to do it correctly. The goal is to keep the base damp, not muddy. Standing water creates a different problem. It can dilute the cement paste at the bottom of the slab, weakening that area and contributing to curling or warping. Then the bottom becomes weaker than the top, allowing the slab to bend, curl, and eventually crack beneath its own weight. A better approach is to soak the subgrade the night before the pour, then give it a light mist shortly before the concrete arrives. That keeps the base cooler, saturated, and ready for concrete, without leaving puddles behind. Instead of stealing water from your slab, the ground becomes part of your defense. Part 5. The Thermal Shock Myth. You'll often hear advice online telling you to spray fresh concrete with a garden hose every few hours. It sounds simple, but if you do it incorrectly, you can seriously damage the slab. Spraying cold water onto hot concrete can cause flaking, scaling, and cracking because of thermal shock. On a brutally hot day, the combination of direct sunlight and hydration heat can push concrete temperatures beyond 110 degrees Fahrenheit. Now imagine suddenly spraying that surface with tap water sitting somewhere around 50 degrees Fahrenheit to 60 degrees Fahrenheit. The temperature difference can be enormous. A rapid surface temperature drop of more than 20 degrees Celsius, or about 11 degrees Celsius, creates powerful thermal stresses inside the slab. The cold water forces the delicate surface paste to contract quickly, while the hotter concrete, deeper inside, remains expanded. Those two layers begin pulling against each other. That tension can tear the weak surface apart, creating crazing, delamination, scaling, or flaking. And there is another rule you should never forget. Never spray water onto concrete while you are finishing it. That extra water dilutes the surface paste, raises the water-to-cement ratio, and can leave behind a weak, dusty surface. Does that mean wet curing is bad? Absolutely not. Proper wet curing is one of the gold standards of concrete construction. But the key word is continuous. Wet curing needs to remain continuous, rather than switching repeatedly between wet and dry conditions. Repeated wet-dry cycles can produce severe temperature changes and thermal stresses that may become worse than providing no wet curing at all. For proper wet curing, soak burlap or curing blankets and place them over the slab, then cover everything with plastic sheeting. This keeps the concrete continuously cool and moist for about 7 days, while avoiding sudden thermal shock. Part 6. Designing the Summer Mix. Chemical Allies and Fly Ash. When you know you're going into battle against brutal weather, you don't wait until the fighting starts to make a plan. You prepare before leaving the base. With concrete, that means designing the right mixture before the truck ever leaves the batch plant. Whether you're mixing concrete yourself or ordering it from a local ready-mix supplier, understand one important point. A standard winter mix can fail badly when exposed to intense summer heat. You need concrete designed to adapt to those conditions. One of your strongest allies is fly ash, either Class F or Class C, or slag cement known as GGBFS. When these materials replace roughly 20% to 30% of ordinary Portland cement, they change the behavior of the mix. Standard Portland cement hydrates quickly and releases significant heat early in the reaction. Replacing 20% to 30% of that cement with fly ash slows the process. Its spherical particles also behave almost like tiny ball bearings inside the mixture, reducing water demand by roughly 5 to 10% while lowering the peak reaction temperature and helping reduce thermal cracking. Your second layer of protection comes from chemical admixtures. The first is a set retarder. This admixture temporarily slows the hydration reaction, extending your working time and allowing the concrete to remain plastic and finishable even when temperatures are high. Next comes a water reducer, also called a plasticizer. If the concrete begins losing slump on site, resist the temptation to simply add more water. Adding 1 gallon of water per cubic yard can reduce strength by roughly 10%, while increasing shrinkage by about 20%. A water-reducing admixture allows you to maintain workability without paying that price. Finally, if you want another layer of protection, you can specify polypropylene microfibers in the mix. These are millions of tiny synthetic fibers distributed throughout the concrete. Together, they form a three-dimensional reinforcing network. As a microscopic plastic shrinkage crack begins opening in the fresh paste, it encounters those fibers, which help arrest the crack before it can continue spreading. Combine fly ash, retarders, and microfibers, and you begin designing concrete that works with summer heat instead of constantly fighting against it. Part 7. Beating the heat at the plant, the power of ice. Sometimes, even a well-designed mix and a properly prepared subgrade are not enough. Summer temperatures can simply become too extreme. When you are pouring concrete in conditions approaching 100 degrees Celsius, you need direct control over the temperature of the concrete before it reaches the forms. The American Concrete Institute, through ACI 301, places strict limits on concrete temperature at discharge. The concrete should never exceed roughly 90 degrees Celsius to 95 degrees Celsius or 32 degrees Celsius. If the batch arrives hotter than that, it should be rejected. The solution comes down to thermal physics and the remarkable heat capacity of water. Water can absorb an enormous amount of heat, which means one of the most effective ways to lower fresh concrete temperature is by cooling the liquid portion of the mix. Batch plants can use chilled water at approximately 4 degrees Celsius to 10 degrees Celsius. During extreme heat, they may go even further and replace part, or even all, of the mixing water with crushed or flake ice. As that ice melts while the truck is traveling, it absorbs tremendous amounts of heat. The concrete can then arrive at the job site around 70 degrees Fahrenheit to 80 degrees Fahrenheit, even when outdoor temperatures are close to 100 degrees Fahrenheit. That cooler starting temperature gives workers precious additional finishing time while reducing the conditions that encourage cracking. If you're a DIY builder mixing concrete on site, you can use the same principle in simpler ways. Keep your sand and gravel piles shaded whenever possible, or spray them with water so evaporative cooling can pull heat away. Cooling the aggregates is especially effective because they make up roughly 70% to 80% of the total concrete mixture. A 2 degrees Fahrenheit decrease in aggregate temperature can lower fresh concrete temperature by approximately 1 degrees Fahrenheit. And then there is one of the simplest strategies of all. Change your schedule. Avoid pouring during the hottest part of the day. Start early in the morning, or work later in the evening, giving the fresh concrete a cooler, calmer window to begin gaining strength. Part 8. Early Entry Secrets, the Green Zone, and Control Joints. There is one basic truth of material science every builder eventually has to accept. Every concrete slab is going to crack. The question isn't really whether it will crack. The question is where. Concrete naturally shrinks as it cures. Without a planned weak point to release that stress, the slab will eventually create its own crack wherever the stress becomes greatest. That is exactly why we cut control joints. Control joints are intentionally created weak points, typically cut to about 1/4 of the slab's depth, reducing the cross-section by roughly 25% to 30%. As the concrete shrinks, the stress is encouraged to create its crack inside that joint rather than randomly across the visible slab. But during summer, cutting those joints becomes a race against time. Cut too early, and the saw blade can ravel the edges, tearing soft aggregate from the fresh cement paste and leaving an ugly, ragged cut. Wait too long and the slab may already have cracked somewhere else. At that point, your saw cut becomes almost meaningless. Traditional walk-behind wet-cutting saws are heavy and normally require the concrete to harden considerably before cutting can begin. That often means waiting somewhere between 6 and 18 hours after the pour. In summer heat, waiting that long can become a serious gamble. One solution to this race is early entry dry cutting, a method pioneered by the soft cut system. Early entry soft cut saws use a spring-loaded skid plate that holds the fragile surface paste in place while the blade cuts, helping prevent chipping along the edges. This allows the joint to be cut during what is known as the green zone, roughly 1 to 3 hours after finishing, when the slab has become firm enough to walk on, but remains soft enough for a clean cut. When operating a soft-cut saw, there are several professional practices worth following. First, choose the correct blade color. Soft-cut blades are color-coded according to aggregate hardness: purple for hard aggregate, green for medium, and orange for soft. Second, break in the blade properly. For the first 100 linear feet, operate a new blade at roughly half your normal forward speed. This gives the diamonds time to expose correctly, allowing the blade to cut efficiently and helping extend its working life. Third, never walk directly along the joint lines while cutting. Fourth, replace the skid plate whenever you replace the blade. A worn skid plate can no longer protect the delicate joint edges properly, increasing the risk of spalling. And fifth, always sweep in the same direction as the joints. Never sweep across fresh cuts, because doing so can damage those fragile green edges. For typical residential slabs, control joints should be spaced approximately 24 to 30 times the thickness of the slab. For a standard 4-inch or 100 mm slab, that means placing joints roughly every 8 to 10 feet, or about 2.4 to 3.0 meters. Keep each panel as close to square as possible, and avoid a length-to-width ratio greater than 1.5 to 1. After about 28 days, seal the joints using polyurethane or silicone. This helps prevent water from penetrating the joint and causing freeze-thaw damage, while also keeping rocks and debris from becoming packed inside and contributing to buckling. Conclusion: building to last. At the end of the day, working with concrete is a powerful reminder of our relationship with the natural world. It is a heavy, beautiful dance between what we design with our own hands and the relentless laws of chemistry and climate. Summer does not have to become the enemy of your concrete projects. High temperatures, dry winds, and direct sunlight are simply variables, forces that can be understood, calculated, managed, and ultimately brought into balance. When we take the time to prepare the subgrade properly, cool our materials, design a mix that can handle the conditions, cure the slab aggressively and patiently, and guide those inevitable cracks through precise timing, we're doing far more than simply pouring concrete. We're practicing the ancient craft of building things that are meant to last. We're honoring our roots, and that is exactly what Survival Roots is about. It's about reclaiming the knowledge we need to build our own lives, our own shelters, and our own futures with our own two hands, grounded in science, respect for the elements, and a commitment to doing the job right. What about you? Have you ever watched one of your concrete projects develop a crack? Or are you preparing for a summer pour right now? Tell me about it in the comments below. Let's learn from each other's experiences. And if you found value in today's journey, hit that subscribe button, give the video a thumbs up, and share it with someone who's planning to build this summer. Until next time, keep your hands dirty, keep your mind open, and keep building your foundations strong. I'm Survival Roots, and I'll see you in the next one.